Hi everyone. So in this video we will be going into a little bit more detail about the shear stress tensor and we'll be doing a derivation to prove that it is symmetric. Uh, but before I go, let us just quickly recap Navier-Stokes equation. So we know that Navier-Stokes equation, it is rho del v vector by del t plus v dot del v vector is minus grad p plus mu del square v vector plus rho g vector. And we have discussed in the class that this has three parts. The left hand side is basically the rho a vector or the acceleration part. The second part, which is minus grad p plus mu del square v vector, is actually the surface force part, or which is del dot sigma tensor. And this third part is actually this body force or the rho g vector or the gravitational force part. So this is something we have derived in class. We have also uploaded a video which goes into detail about each term. So if you're unfamiliar, please go ahead and go through the notes and the video. But what we will want to focus on in this video is this term, is this minus grad p plus mu del square v vector term. So like I said that del dot sigma is actually equal to minus grad p plus mu del square v vector, and sigma tensor in itself is actually has 9 components. Sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. And we say that sigma can also be written as minus p 1 0 0 0 1 0 0 0 1 plus tau xx, tau xy, tau xz, sorry, this is tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. Right? So the sigma tensor, which is basically is a tensor because we need two directions to define a force, surface force. One direction is to define the surface, that is to define the surface normal. The second is the direction of the force. The first subscript here is the direction of this surface normal, and this is the direction of the force. And we say that the surface stress tensor sigma has two parts, pressure part and the shear stress part. The pressure part only has diagonal elements because the pressure force is only normal. So the surface normal direction and the force direction is only same in the diagonal elements. So that's why this only has diagonal parts. Tau in general has all the 9 components there. Okay. So when you take del dot sigma, this becomes minus grad p plus mu del square v. You can also write this as minus grad p plus mu plus del dot tau. So the mu del square v term is actually equal to del dot tau. Okay, so basically any surface stress has two parts, pressure part and tau part, and what we want to do in this video is go into more details about this tau part. Okay, so let's go in more detail about tau. So tau has been defined as 2 mu gamma tensor. So let's just go back, forget about any derivation about Navier-Stokes, and just remember that whenever we discuss tau in the first part of the course, we were trying to get a scale of shear stress. We used to say that it is equal to mu u by h, where mu was the viscosity, u was the velocity, and h was the length scale. So we can also call this as mu into gamma, where gamma is the strain rate and has units of second inverse. Okay, so that gamma is actually this gamma tensor or velocity by length. Okay, and gamma is defined in terms of velocity is defined like where del v is the outer product of gradient and velocity, and outer product of two vectors gives back a tensor. So tau is a tensor, so gamma has to be a tensor because mu is a scalar, and since gamma is a tensor here, del b has to be a tensor, and this is just the transpose of the same outer product of the vector. Outer product of the two vectors, which is a tensor. So this is the transpose of that tensor. And of course, you can imagine that we will only take transpose when we have a symmetric matrix. That means that we have 3 cross 3 or 2 cross 2, right? So that's only when we can take transpose. So del v is actually a matrix. So if we expand this product, we can actually write in Cartesian coordinates gamma tensor in terms of vx v by vz as follows. So you can see that because it is a half and del v, this has del bx by del y, this part, and then if you have the del dy by del x comes from this transpose term, right? And then we have a half. So because we have a transpose adding, we have x by y and y by x both. Similarly, x by z and z by x. Okay, so we can continue writing, and this will be half del by del x plus del bx by del y, half del vz by del x plus del vz by del vx by del z. Here it will be half del v z by del y plus del vy by del z, and it will be half del vy by del z plus del vz by del y. Okay, so basically because of adding transpose, this term becomes equal to this term become equal to this term becomes equal to this term, or it becomes a symmetric. So these two and these two are same, so it becomes a symmetric, or sigma gamma ij becomes equal to gamma ji. Okay, so now we have a gamma tensor which is symmetric, or that means that gamma is symmetric, right? Similarly, now once we know gamma, we can calculate tau. So tau will be nothing but 2 mu times this whole matrix, right? Whole matrix. Just we'll multiply everything by 2 mu and we'll get tau. So now that means that tau is also symmetric, right? Or in other words, tau ij will be equal to tau ji, because gamma is symmetric. Because gamma ij is equal to gamma ji, we'll have tau also symmetric. And recall that the the total stress tensor is minus p delta plus tau, or minus p into 1 0 0 0 1 0 or 0 0 1 plus tau xy sorry tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. So we know because tau is symmetric, these two will be same, these two will be same, and these two will be same. If we add tau in sigma and basically add pressure here, this will become minus p plus tau xx minus p plus tau yy minus p plus tau zz, and then we'll have tau xy, tau yx, tau zx, tau zy, tau yz, tau xz. So because gamma is symmetric, or the shear strain tensor is symmetric, uh, shear stress tensor is symmetric, and because shear stress tensor is symmetric, we can see that even this is symmetric because the off diagonal component only has shear stress. Pressure is only in the normal part, so even sigma stress is symmetric. So let's recall what we have said, that gamma is symmetric, implies tau is symmetric, and that implies sigma is symmetric. And why is that? Why is that important? That important is because let's say you have a velocity profile, right? And if you have a velocity profile, then you can calculate this strain rate tensor, because if you have velocity vector vx ex plus vy ey plus vz ez, and then you can just take derivatives with x, y, and z and calculate this strain rate tensor. And but you don't have to calculate each and every term. Once you have calculated this term, you will have this term as the same. So basically, it saves work. So you only need 6 unique expressions. You do not need 9 because 3 of them are same. Like 3 out of 6 are basically repetitive. So you don't have to do more work than you need to. So once you have calculated tau, let's say xy or gamma xy, the gamma yx will be the same. And I refer you to table in 6.4, 6.5, and 6.6 in the book to see relationship between tau is equal to 2 mu gamma in different coordinates. And there again you can go and check that tau is symmetric. So if you have the velocity profile, you can actually evaluate these things very easily. So we have given a mathematical reason of why gamma is symmetric, why tau is symmetric, and why sigma is symmetric, but we have not given any physical meaning to that. So we have basically explained that in Navier-Stokes equation, this part is dependent on del dot tau, which is a symmetric tensor, and that makes gamma also symmetric. And tau is symmetric because gamma tensor is symmetric because that's a sum of outer product of gradient and velocity, and it also has transpose in it added to it. So because transpose is added, gamma becomes symmetric, so tau becomes symmetric, and so sigma becomes symmetric. This is just a mathematical reason. There is no physical feeling to it, and a lot of students get confused at why tau yx should be equal to tau xy. Like, why should a shear force in because tau xy, like we have discussed, tau xy is uh, the stress on a surface with normal x acting in the y direction, and this is shear stress normal to a surface with y and acting in x direction. Why should they be same? And that's a very valid question, and even during my undergrad studies I would very often get confused in this. And the actual reason for this to be symmetric can be understood by uh, doing a torque balance. So this is something we have not done in the class. So on a fluid system, surface torques are also balanced. In other words, if we have an element of, of, of a fluid, let's say we have, this time we'll take a cubical element rather than a cuboidal to make our life a little bit easy. So let's call this as L, this is L, and this is L, and this direction is X, this is Y, and this is Z. Sorry, make it a little more clear. I'm saying that surface torques are balanced, and let's have, it does not look like a cube, but assume this is a cube. Okay. Uh, and that this direction is y, this is z, and this is x. Okay, and if the fluid element was toppling or it was rotating, we'll have surface torques are not balanced. Because the fluid element is not rotating, surface torques have to be balanced. And because of that, we can actually prove that tau is symmetric or sigma is symmetric, because tau is symmetric, so means that sigma is symmetric. So let us have this surface ABCD here, and let us have the surface EFGH. Okay. So now what we want to do is what we want to find is that R cross S of n vector times PS over L cube is equal to 0. So now this is a heavy expression. Let's go one by one. So this integral basically means it is on 6 different surfaces. So the cube has 6 surfaces. So we're integrating over 6 surfaces. Sn ds is the force on one surface. So we know that Sn is basically the force exerted by fluid with normal n vector, uh, and that basically Sn is n dot sigma. This is something we had discussed in class, and this was also reviewed in the last video of review of Navier-Stokes. So please go ahead and see this. And this r is the vector distance or distance vector or the length vector from center of cube to surface, right? So we are trying to write the torque on this from this, basically using center of the cube as the point of rotation. So we're saying that because any torque is this r vector cross force, and then we are saying per unit volume basis this should be 0, right? So this makes a lot of intuitive sense, that basically we have a length cross force by this is just per unit volume basis, and if we sum on all the 6 surfaces, we should have net, this should net be 0. Now let us have the ABCD force, sorry, surface. Let's write this expression for first ABCD. Now the in ABCD, the r vector from the surface or from the center of this to on this surface ABCD would be, length would be minus L by 2, and the direction of this vector is negative of x direction, right? So this will become minus L by 2 ex, because this is going negative of x, so this will be minus negative by 2 minus L by 2 ex. Okay, the n vector, so n vector is the vector pointing into the fluid, but here the fluid element which is applying torque is not this fluid element but the outer fluid. So the normal to the surface pointing into the fluid is the outer system, because we are calculating torque on this fluid. So n will be away from the surface because we are pointing into the outer fluid. So n will also be minus ax. Okay, so s of minus ex is n dot sigma. So n is minus 100 times sigma tensor, sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. So if we do that, this will clearly become, so what, to multiply matrices, we take this and multiply piecewise by this part and add, and then that will become the x component. This is minus sigma xx ex. Then you take and multiply by this part, and you will have sigma xy ey and sigma xz ez. Okay, xz ez. Alright, so now we have s, we have r, So we can start to calculate, and ds is nothing but L square. The area would be L square when we integrate. Okay, so the r cross n, sorry, r cross s of n s of n ds on ABCD is equal to r is minus L by 2 ex cross minus sigma exx ex minus sigma xy ey minus sigma xz ez times L square by L cube, right? And if you do that, this actually becomes half because L cube gets cancelled. Right? L cube gets cancelled and minus minus gets cancelled. So this becomes ex cross sigma xx ex sigma xy ey sigma xz ez, and ex cross ex is 0. So cross product of x with x is 0, x with y is z, and x with z is minus ey. So again, once again, x with x is 0, x with y, x cross y is z, and x cross z is minus y. So this actually becomes sigma xy ez minus sigma xz ey. Please make sure and check that you are also getting the same expression when you do the cross product. So now we have something, and this is evaluated at x because we are keeping x constant, right? So this is for the surface ABCD. Similarly, we can write the expression for DEFG, sorry, EFGH, my mistake, for the surface EFGH. EFGH, and for EFGH the R vector would be flipped, right? And so would be the N vector, because R vector for EFGH would be plus L by 2 Ex, and the normal vector will be pointing into the fluid of the outer fluid, and that will also be plus. So technically R is also reversed and N is also reversed, so you get the same expression. However, now the difference is that you will be evaluating this at x plus L. Right? So we have written for two surfaces. Now we can note a pattern and write this for the entire system. So we can have two components. We need cis components. So let's look at the pattern. So the pattern is you need x, y, z. So the two components here have x, y, and then you will have z. And if you have x, z here, so the you should remember the cyclic property of x, y, z. So whenever you have the two items here, x, y, then you have z. If you have x and z, you go in the opposite cycle. So you'd go x, z, y and put a negative sign here. Okay, so let's see. X, y, z, x, y, z. And if you go x, z, y, then you put a negative sign because you're going in the opposite cycle. So let's try to write quickly without doing any math the balance on HADG. Okay, HADG. So how will we start? HADG is has a normal in y direction. So HADG, this one, has a normal in y direction. So what we can do is we can write HADG as a normal in y direction. So our here we will get EX and EY. So we'll have EX and EY, right? So we'll have sigma YZ EX, right? Because we have to get, sorry, I meant here EZ, because the normal was in y direction. So if the normal was in x direction here, you only had z and y component. If the normal is in y direction here, you will only have x and z component. So y z x minus, you will have minus y x z. So initially you will have to get a y here, and at the end you need x and z. So y z x, so you are in the cycle y z x, and if you go y x, then you have to get the cycle in the opposite direction and have a negative sign. Okay, and this is evaluated y. Similarly, HADG EBCF will have the same expression but evaluated at EBCF with the same expression evaluated at y plus L, right? So I'm not going through that. Then let's just do one more. We can do for the z component. Let's go for ABEH. This component, the bottom ABEH, ABEH, right? So here we have the normal in the z component, so we'll have EX and EY, right? So we need sigma x, sorry, so sigma z, because the first direction will always be z because the normal is in z. So we have zy. So if we are going zy, then we are going opposite in the cycle. So we'll put a negative sign here, negative sign, plus sigma z x y. Okay, and gxy you can see is in the same cycle. So this is just a symmetric way of putting things. Z, the last surface will have same expression but evaluated g plus. So we have all the six contributions now. So we have 1, 2, 3, 4, 5, 6 contributions now, and we have to sum everything to get the right balance of torque on the entire system. So if you sum all of this, if you do summation, all the terms, and take limit L equal to 0. So if you take limit L equal to 0, we should note that these two would basically become same, because z plus L is going to be the same as this, so it will become the same. So half and half will combine and become 1. Similarly, these two will become same, and these two will become same, right? Half and half will become 1. So if you do that, and x plus and x plus L will vanish. So if I combine all these terms, and then I have EZ here and I have EZ here, I have EY here and I have EY here. So if I basically club the same directions, then what we will get is basically sigma xy minus sigma yx into EZ plus sigma yz minus sigma zy into EX plus sigma zx minus sigma xz into EY. And we know this is equal to a 0 vector because the torque has to be balanced. In other words, xy, sigma xy equal to sigma yx, sigma y equal to sigma zy, and sigma zx is equal to sigma xz. So what this derivation was trying to do was trying to tell you that if you apply a torque on a cube of a fluid element, the stresses have because the force that will come out of the stress has to be such that the system cannot rotate or cannot topple. That's why they have to be symmetric, and which is now intuitive. So if you think about it, that the yx and the xy component will create the torque in the same direction, right? So that's the beauty of this being symmetric. So the xy component will create the torque in the z component, because xy will, because we are crossing, and xy will be component will be have a normal such that we'll get the z component. So if you see here, the xy is with z and similarly yx is z. So they will create the torque in the same direction, and because the torque has to go 0, they actually balance each other out. So physically, whenever you understand tau is symmetric, it is because the torque has to be balanced, or the system cannot have any rotational component on it on each element. So let us recap whatever we had discussed till now. So we started by talking about the Navier-Stokes equation, and that Navier-Stokes equation has three parts: the acceleration part, the surface part, and the gravitational part, and that the surface part can be thought of as pressure part and this del dot tau part, where tau is this shear stress tensor, and sigma can be thought of as minus p plus tau. Minus p only has diagonal components because it is normal, and negative because it is compressive. Then tau should be thought of as mu u by h, or mu into some strain, which is unit of second inverse. And that's why when we write in vector tensor form, we have tau is 2 mu gamma. Gamma is a tensor, and gamma is a symmetric tensor of velocity gradients, which is this complicated looking matrix. Whenever you have a velocity profile, you only have to calculate 6 unique systems because it is a symmetric system, or gamma ij is gamma ji. So if you have calculated gamma xy, you don't need to calculate gamma yx. Okay, because gamma is symmetric, tau is symmetric, and because tau is symmetric, sigma is symmetric. So that's what we showed by calculating everything here, that tau is symmetric, so sigma is symmetric. Now, to give a physical meaning of that, we said let us go and do a torque. Torque is length vector into, or the distance vector into force, cross with force. So force on one surface is calculated by Sn, where n is n or n dot sigma, uh, and we will basically do this and get it on all 6 different surfaces. So we started by having first surface A, B, C, D, and found R and N. Once we have N, we can calculate S, which is n dot sigma, and once you have that, we can calculate the contribution from one of the surfaces. By using the symmetry argument, we calculated this on all the 6 different surfaces, and when you add, basically you get that when you add each direction, whichever produces torque has sigma xy and yx, sigma yz and zy, sigma zx and zx and xz, and they have to balance each other out for the tau to be for the fluid element to not topple. So I hope that this video gave you a little bit more flavor about the tau vector and the origin of its symmetry, both mathematically, how you can derive it from a strain rate tensor using velocity profile, or from a physical meaning from torque balance. So I hope this video was useful, and please feel free to give us any feedback.